Thank you all for joining us today. This webinar will be recorded. This is the 2021 SPS Intern Symposium. Hi, I'm Brad Conrad. I'm the director of SPS, and I'm really happy to have you all join us today. We're going to hear some awesome talks from some amazing SPS summer interns this summer. But before we get started, I'd like to introduce the CEO of the American Institute of Physics, AIP, Michael Maloney. Michael?
Thanks, Brad. Thanks, Kayla. Hi, team of interns. Great to see you this morning, and good morning to everybody else, or good afternoon, good evening, wherever you might be in the world. That's the Zoom world we live in today. So, yeah, I'm not going to keep you all waiting for the main show this evening or this morning, speaking with or hearing from the interns. But I did just want to say how much we really appreciate the opportunity to interact with such a tremendous, inspiring set of folks who are the future of physics, astronomy, and the physical sciences, and our community going forward into the future. So it's really a fantastic opportunity for us every 10 weeks at AIP to get a glimpse into the future and the tremendous opportunity that our field has, our fields of endeavor have for the future. So this program is supported by AIP, and SPS is an integral part of the AIP family, along with AIP Foundation, AIP Publishing, and our 10 member societies and 27 affiliated societies. And the intern program is really a partnership between those partners and donors, and as I mentioned, are the societies in particular that are focused on this internship. And this year, that's the American Physical Society, the American Association of Physics Teachers, and the Society of Rheology. Also really want to thank Sigma Pi Sigma members, NIST, NASA, the US House Commerce Committee on Science, Space, and Technology for their partnership in the internship program, and also extremely grateful for the support of donors, and in particular, the John and Jane Mather Foundation for Science and the Arts for their ongoing personal and philanthropic support of this program and our mission at SPS to support the future of our science through our interactions with the undergraduate community. So I know from a quick chat before this call today, and then also from my discussions with previous classes of interns, that one of the real key important parts of the internship program is to give insight into the full suite of career opportunities that lie for in the future for people who study physics, astronomy, and related sciences. And so again, thanks to everybody who's helped make that an experience, which I know this class of interns will carry forward with them into their careers. And special thanks to Brad and Kayla and the rest of the SPS national team, and also our volunteers at SPS and Sigma Pi Sigma, our volunteer leadership, who really are such tremendous support to us in our endeavors. So thanks again, Brad, for the opportunity to say hi. I look forward to watching as many of the talks as I can today, and good luck with the rest of the program.
Thank you, Michael. And I just wanted to add a couple of my own comments. So I wanted to thank all of the interns for joining us this summer. The summer is not complete without you and all of the hard work that you do and all of the energy that you bring and the programs that you help start and finish and add that special touch and flair that only interns can really do. Because when you're doing something for a long time, you sort of get used to doing it a certain way, and you always come in with bright new ideas and interesting ways of making things happen. And most importantly, we're aiming to serve you, because you are the Society of Physics students. You are the next generation of people to come into the field. So we're really happy to have you join us. And I did also want to tell you this is a very prestigious program. It goes back to 1999. It actually started off as a single intern. If you can imagine being the only intern, that might be a little challenging. They were focused on 2-year school preparation and education and outreach, and the program has gotten a little bit bigger since then, but it is a very prestigious program. And so We're able to do not just education, but we're able to do science policy and research and outreach and work at national labs and do experimental physics and theoretical and all of these different things. And the magic, the reason why I'm really proud of this program, is that each of you had a different kind of internship. But yet you all were interacting with each other through the virtual events we had over the summer and talking with each other and the social nights and all of those things. So even if you might have been at NASA, you still know what it's like a little bit to be at Capitol Hill. Or if you're working for the American Association of Physics Teachers, you know what it's like to do outreach or what it's like to do theoretical astrophysics research at NASA. So all of you get to share a little bit, and that's part of the magic. And so everybody knows every intern is encouraged to share their research or their summer experiences online on the website, so you can check out the blogs. They're really great. I did promise I wouldn't read my intern's blog until the very end, so no, I'm going to read yours as soon as this is done. But it does give you a window into what it's like to be an intern in 2021 and what they learned and what they experienced. So I'm going to turn it over to Kayla.
Thank you, Brad. Hi, everyone. Welcome. I'm Kayla Stevens. I'm the SPS Assistant Director, and I have the privilege of introducing all of our interns today. You can find the program in the chat, so please follow along. There is a slight change. We are actually going to start off with a very special demo that was created by our interns, and our stock intern, Noah Johnson, will be introducing it.
Yeah, so thank you all for joining. And so we'll be watching the demo competition for the AEPT summer meeting this past summer. It just happened last weekend, and it was a lot of fun to make. All the interns created these epic and awesome demos and demonstrations that I was able to compile into a demo competition video. They're all fantastic, and so we hope you enjoy.
Great, awesome. Thank you so much, Noah. That was absolutely amazing. I have so much fun watching that each time I watched it, and I watched it a lot. So we will go ahead and get started with our first presenter. We have Jess Zelda from the Society of Rheology Soft Matter Kitchen, and the floor is yours.
Awesome. Thanks so much for the introduction, Kayla. It says that you have disabled participant screen sharing.
One second, technical difficulties. I'll be right with you.
Awesome. Hello, everyone. My name is Jess. Today I'm going to be talking to you about bringing the lab home, the physics of cooking at the Soft Matter Kitchen. So this summer, I worked with the Society of Rheology and Arif Nelson on this awesome educational outreach project called the Soft Matter Kitchen, and I'm going to talk to you a little bit about it. So to start off, I'm going to ask a simple question. Which is more viscous, honey or mayonnaise? So at first glance, this seems like a pretty simple question to answer, right? We think of viscosity as this resistance to flow. So we can take a small sample of each the honey and the mayonnaise and put it on a spoon and turn it sideways. And when we do this, we see that the honey flows readily, whereas the mayonnaise barely flows at all. So we would say the mayonnaise has a much higher viscosity. It resists flow much more. But what if we take these same samples and put them in a little bit of a different situation? So I'm going to take a sample of each the honey and the mayonnaise and put it between my fingers, and then begin to apply a shearing force circularly around it. And as you can see, in this case, the honey maintains a lot of that stickiness, that viscosity, that resistance to flow in the first, when you rub it in between your fingers, but the mayonnaise readily flows away from the center of my fingers in either direction. So this is an example of what we call shear thinning. So in a typical Newtonian fluid that we think about, viscosity is this constant thing that doesn't depend on any other factors except maybe temperature. But not all fluids follow these simple rules. In fact, fluids like this mayonnaise can change their viscosity dramatically as different amounts of stress are applied. So here we've plotted viscosity against stress for a shear thinning fluid, and you can see that the viscosity drops by many orders of magnitude as additional stress is applied. So as I mentioned, a Newtonian fluid would just experience a constant viscosity the whole time. So rheology is really the study of these complex, non-Newtonian fluids that don't obey these simple equations like the one shown on bottom here. So this is Newton's constitutive equation, and it tells us that Newtonian fluids, their rate of strain is proportional to the stress applied, with the proportionality constant just being this constant viscosity. But rheologically interesting fluids don't show this simple behavior. So a good way to think about it is that while fluid dynamics studies simple fluids in complex flows, rheology looks at complex fluids in simple flows. So it's projects like this that I've been working on this summer at the Soft Matter Kitchen, an educational initiative where we try to explain complex rheological concepts like shear thinning using something people see every day, namely food. It turns out that cooking and eating, there's all kinds of rheologically interesting behavior going on there, and it can be a really good lens to show people what this field of rheology looks like on a very visceral way that they have some experience with. So the project mostly consists of a blog, which is hosted at arif.zone, as well as video content, and we've had 600 visitors this year, 600 visits this year from 400 unique visitors, which is up a lot from last year. So getting back to the mayonnaise a little bit, we saw that this mayonnaise was a shear thinning fluid. In fact, it goes a little further. We consider it a yield stress fluid because below some critical stress, the mayonnaise actually doesn't flow at all. The viscosity looks like it's going off to infinity. It acts very much solid. What makes the mayonnaise have this weird behavior? So look at this, we need to zoom in a little bit. So this right here is a picture of the microstructure of mayonnaise. So as you can see from the scale bar, this is about one of these bubbles, over droplets we call them, is about 70 micrometers across. And it turns out that this sort of micro scale is where almost all rheological properties arise. So what's happening in the mayonnaise is it's an emulsion. That means it's a combination of two things that don't normally like to mix. In this case, water and oil, the mixing is facilitated by some emulsifier. So as we rapidly mix the oil into the water, what happens is the oil forms droplets, as you can see in this picture, and those droplets jam up against each other. So at low amounts of stress applied, these droplets jam against each other and resist each other and make flow very, very hard, cause a high viscosity. But as a significant shearing force is applied, the droplets are able to slide past each other in that medium, causing that shear thinning behavior. So, sorry about that. So this is an example of how rheology can be used to understand something that we do in the kitchen, but rheology can also be used to design things that we do in the kitchen. In fact, rheological considerations play a big role in a lot of industrial food processing, industrial design, as well as in things like modernist cooking, where processes like spherification are really popular. So to sort of talk about this, I'm going to talk about a project that I did this summer on rheological design in tiger stripe milk tea. So this is a really popular drink. It's a boba drink that's gotten really big. It's spread out of Taiwan across the world, and it's famous for these distinctive stripes across the side of the glass. So I decided to try to recreate this. So for my first attempt, I just boiled some boba in brown sugar to make a syrup, and then attempted to use that syrup to coat the side of the glass. As you can see, it was a rather poor coating. So I thought, how can I use rheology to measure the properties of this syrup and then design a better one? So one thing that I noticed is that the syrup had a substantial amount of elasticity, significantly more elasticity than a typical just sugar syrup. And you can see that here, the syrup stretches. And elasticity is another property that we don't see in Newtonian fluids, but that's very important in rheologically interesting ones. So I thought this elasticity was likely due to a starch network that was forming in the syrup. Starches, as can be seen in the center photo, are known to give a significant amount of elasticity, and tapioca, which boba is made from, is a great source of starch. So to rheologically design this fluid, I tuned the amount of starch. I decided to add extra starch to my syrup and tuned the amount to get something with substantially more elasticity to the syrup. And when doing so, I was able to get a much better coating that looked a lot more like the tiger stripe coating I was going for. So that's just one example of how rheology can be used to design the foods that we eat, as well as just to experiment on them. Thanks so much, and I'm happy to take any questions.
Awesome talk. So I'll start off. First question. So when you were going back to the tiger tea that you made, can you talk a little bit more about what's causing the striping pattern, or if you know why that striping pattern exists?
Yeah, so the striping pattern basically happens from the coating process. There's at Tiger Sugar, which originated this drink, they have a proprietary coating process to such a degree that there's only 2 people in the shop who know how to do it, who do it in a back room and then hand the pre-coated cups out to the people up front. So the exact process they use is a little unclear to me. What I found had the best results to get sort of a distinctive stripe pattern, like you see here, or at least an interesting looking one, was to coat boba in the syrup and then run them down the sides of the glass as I put them into the bottom to form that initial pattern. And then the elasticity helped that pattern stay on the side of the glass instead of melding into a sort of a uniform coating on the side.
Awesome, thank you. And second question. Can you think of any fun or interesting applications for the boba syrup due to its high elasticity? Perhaps we can make some kind of glue or something for industrial purposes?
Yeah, that's a great question. So there's a lot of really cool things that you can do with elastic fluids. If we wanted to make some kind of food safe glue, can come all of like modernist cooking projects where people want things to stick in weird shapes that they couldn't otherwise do. this certainly has the advantage of also being delicious. It's a sugar-based syrup, so I think it could have some great applications in some kind of complex dessert where you wanted something to stick to the side of a glass in an unintuitive way.
Awesome. Well, thank you for an amazing talk. I appreciate it.
Yeah, thanks so much.
Okay. Kayla?
Yes. Now, thank you so much again, Jess. Moving to our next talk, we have Karthik Rao from NIST and Texas A&M University. Karthik?
All right. Let's see. So, hey everyone. I was one of the NIST interns this summer, and I worked in the Advanced Electronics group. And I performed simulations using COMSOL, where I profiled the shape of electrostatic force microscopy probes. And here's a bit about what I did. So what is electrostatic force microscopy? So let's begin with scanning probe microscopy, which is a technique that forms images of surfaces using a physical probe to scan specimen. Atomic force microscopy is a more specific technique that generates very high resolution images by using a cantilever to scan over the surface of the sample. When the tip is brought in proximity to your sample surface, forces between the tip and the surface cause the cantilever to oscillate. And depending on the situation, forces can be electrostatic, mechanical, magnetic, and more. Now, electrostatic force microscopy, which was something that we were interested in, is a non-contact atomic force microscopy technique, which gives us access to the electrostatic properties of samples with high precision. And the way this technique works is you apply a bias voltage to excite the cantilever and make it oscillate, and you basically measure the force with which it's oscillating. Now, this technique is dynamic because the cantilever is not actually making physical contact with the surface, but despite this, you get very high resolution images. So I use COMSOL to perform several simulations of electrostatic force microscopy. And COMSOL is basically a general purpose simulation software that uses finite element methods to solve basically partial differential equations. And the way this works is you set up your environment, you define studies, and you can set out to solve Maxwell's equations or other physics-based situations, and you can get results for electrical, mechanical, fluid, and other applications. So here's something about what I did. So I set up these 2D simulations where I had 3 aluminum strips, a platinum probe, and cantilever. And the strips were surrounded in silica, and the probe was in air, and the distance between strips was 0.1 micrometers. Now, the middle strip, which was 0.2 micrometers wide, was biased with 1 volt, and the rest of the strips were grounded. The probe was at 0 volts initially, and it had a 0.1 micrometer distance from the surface. Since I wanted to simulate realistic results, I also added a curved tip to the tip of the probe was curved with a radius of 20 nanometers, and the cantilever was at an angle of 15 degrees, which is what probes that are manufactured usually have. Since my job was to see how the results correlated with the probe shapes, I performed simulations for 4 different probe shapes, one which had the leading edge at 90 degrees, one which had a trailing edge at 90 degrees, one which was symmetric, and one which had a small angle. Here's the study. Here's a little animation of the probe scanning across the surface. And as you can see, the area where it's red is where you have the max voltage, which is 1 volt, and the surrounding areas have blue, which have the least voltage, which is 0 volts. And as you move further from the surface, your voltage decreases. On the right-hand side, you have the mesh that COMSOL creates. And as you can see, it's made up of different elements, which is how COMSOL actually calculates and solves your equations that we needed to solve. And as we go closer to the surface of the middle strip, it creates more and more elements, which is because that's the area that we're interested in. Here are the results that we got from the 4 different probe shapes. And as you can see, that it was the same study, but done with different shapes, and the results varied quite a bit. For instance, the symmetric angle probes that had an equal, that were not, that didn't have any perpendicular edges, were symmetric about the 0 in the x1 direction. On the other hand, the one with the leading edges and the trailing edges were tilted to the left or the right. another thing of interest to note was that the trailing edge, the max voltage found by the trailing edge was not the same as the max voltage that was detected by the leading edge. And this was very interesting to see. Also, the thin angle probe detected far less voltage compared to the others, which may be and one of the reasons was that it was at a very thin angle, far less than what would be appropriate for the situation. So some of the analysis that I did was, first I estimated the background. Since we're measuring the potential at the tip, we wanted to eliminate any potential that was measured by the cantilever itself. So for all the probes, I eliminated the actual tip and I measured by scanning the cantilever over the surface. There wasn't a lot of background, but it was still substantial so that you can see a slight difference between the results with the cantilever and without the cantilever. Then I plotted the potential again that was measured against the probe shapes. And if you just plot the potential, we see there isn't a whole lot of correlation, or it's very difficult to see. Clearly, you can see there's a difference between the trailing edge at 90 degrees and leading edge at 90 degrees, but still, it's not enough to make an assumption about what sort of equation might be relating the potential to the probe shape. So I went ahead and plotted the inverse square root of the potential against the probe shape, and here the difference is much more clear. It appears as if the only difference between the actual inverse square root and the probe shape would be like a constant or a factor of, say, 2 or 3. So especially in the symmetric and the small angle cases, this is much more evident, where if you were to just make this, multiply this by a factor of, say, 2 or half, you would easily overlap with the probe shape itself. So to summarize the results, the tip shape does appear to correlate with the potential being measured. And the relation is the distance, is that the distance which defines tip shape is proportional to the product of a constant and inverse square root of the potential measured. So in future, we would like to use this data to create an algorithm that can give details about the tip shape based on experimental scanning results. And we would also like to perform simulations in 3D to give a more realistic relation between the tip shapes and the resulting voltage distribution. I'd like to thank my mentors at NIST, my fellow interns at SPS, all the staff at SPS and AIP for making this a fun summer. And I'd like to take questions.
Awesome job. Congratulations. And so quick question, how do these results match to any physical experiments or physical systems that you might know of?
So since the since this was virtual, then virtually I didn't have a chance to actually be in lab and look at the experiments, but I'm pretty sure that based on papers that I was reading, that these results do match up in the way that we want them to match up, in the sense that probe shape and the potential being measured is like, the relation does appear to be like an inverse square root relation when you compare it with real like experimental data.
Mm-hmm. And then if you were to be doing experiments, is there a recommended probe shape or probe orientation for these kinds of experiments?
So the ones that are typically manufactured do have a like the angle of the cantilever at 15 degrees. And then I believe we can use either the leading edge at 90 degrees or the trailing edge 90 degrees or the symmetric one. The small angle one was not recommended just because the results were so far different from what we were expecting.
And one last quick question. If you had one piece of advice for yourself 10 weeks ago, what would that be?
I'd say expect to spend a lot more time learning COMSOL than you think, because it's a very complex software, and it takes like so long to actually understand what's going on in there.
Well, you did a great job, and congratulations on an awesome set of research presented. So great job.
Thank you.
Thank you, Karthik. Next, we have our FYI Science Policy News intern, Julia Bauer from Davidson College.
Thanks, Kayla. One moment while I pull this up. Kayla, would you mind just confirming that you can see everything and hear me?
Yes, everything looks great.
Awesome, thank you so much. Good morning, everyone. My name is Julia Bauer, and I was the American Institute of Physics FYI Science Policy News intern this summer. FYI is a federal science policy news and resource center, meaning that our purpose is twofold. We publish a weekly newsletter comprised of short, timely blurbs that track federal science policy developments. We also publish supplemental bulletins that take a deeper dive into science policy. On the other hand, we maintain 3 distinct trackers that document leadership appointments, bills, and budget figures related to science and science policy. So as part of my contributions to the news side of FYI this summer, I had the opportunity to draft and then publish roughly 15 blurbs for our weekly newsletter. So these blurbs spanned a variety of subtopics, including naming conventions at NASA and immigration policies that affect STEM professionals looking to settle in the United States. And of these 15 blurbs, 3 became bulletins. And in addition to being thematically distinct, each one was unique in that it covered or reflected a different stage of the policy implementation process. So for example, my first bulletin, which was co-authored with my mentor, Mitch Ambrose, featured a House Science Committee hearing that was very much geared towards information gathering to inform Representative Zoe Lofgren's legislation to better operationalize wildfire science research to address the increasingly frequent and intense wildfires in the Western United States. My second was representative of sort of the intermediate stages in the policy implementation process and featured 2 separate hearings. And finally, and really interestingly, my third bulletin talked about a program within the Department of Energy, the Low Dose Radiation Research Program, that has been in existence off and on since 1998, which just really goes to show that science policy developments run the gamut in terms of the timeline of policy implementation. So my first bulletin, as I mentioned, was about wildfire research policy and management. So as part of this House Science Committee hearing, they featured 4 wildfire science and policy experts in the field who issued a variety of recommendations to the House Science Committee about how best to combat wildfires, particularly with the advent of climate change. And the most notable recommendation I found was to improve both the temporal and the spatial resolution of satellites that monitor wildfires. Oftentimes, satellite engineers and scientists are forced to balance the 2. So for example, satellites that pass frequently over problem areas have pixel resolutions of 1 to 2 kilometers, which is obviously suboptimal. Ideally, we want to have satellites that are both timely and accurate in terms of their spatial resolution so that we can track wildfires in real time and hopefully prevent their spread. My second bulletin was unique in that it tied together 2 different hearings. The first was the nomination hearing for Shalonda Baker, who it confirmed is set to assume the position of Director of the Office of Economic Impact and Diversity within the Department of Energy. And the second was another House Science Committee meeting that featured experts in the energy equity field or related fields. And we originally flagged both of these hearings because of an interesting thematic link, which is that they both fall under or are related to the Biden administration's Justice 40 initiative or directive, which aims to ensure that at least 40% of select federal investments in climate and clean energy then benefit marginalized and disadvantaged communities across the United States. And I found this really fascinating because I'm very accustomed to thinking about resources like food informing low-income families, like food insecurity and other equity issues. And I've never thought about energy as a resource that's also unequally distributed across racial and socioeconomic groups in the United States. So this was a really informative piece for me, and I enjoyed hearing about witnesses' recommendations to improve access to technologies like solar panels and other renewable energy technologies, which are often developed with homeowners in mind, which then excludes renters and just very unfairly impedes access to those sorts of technologies for certain groups of people. And finally, as I mentioned, my third and last bulletin of my internship experience, which fingers crossed will be published later today, was on the low-dose radiation research program in the DOE. As I mentioned, it was established in the late 90s, was discontinued in 2016, reestablished by Congress in the Energy Act of 2020. And there's just been this continual sort of contention between Congress and bipartisan support in Congress for this program and the Department of Energy, which has historically been reluctant to continue the program. So this was interesting for me in that it shows the sort of like the human aspect of policy. It's not just about the logistics of implementation of a certain program or even appropriations. It's also a matter of whether the hosting department feels like the program is a good fit. And I also found that this was interesting because it talks about, or that the program is very relevant to the linear no threshold theory, which posits that there is increased cancer risk for any dose of radiation, especially even low doses. So I'm interested to see whether this program continues within DOE, another department, and if so, whether it challenges or supports that theory. So with that, I'd just like to say that I found this internship opportunity fascinating. It taught me a lot about the different policy implementation hurdles that sometimes impede the progression of bills through Congress and then eventually becoming law, and that those sorts of hurdles can take a variety of forms. I also enjoyed learning about how science policy can be used to address equity issues, and also how equity can be better built into the science policy process in general, so that places like the DOE are consulting marginalized communities for their expertise and input while developing technologies intended to benefit those communities. And finally, I want to just mention how much I feel I've grown as a writer this summer. And I'd like to thank the wonderful people who gave me lots of feedback this summer, who taught me how to better distance myself from my writing so I can consider different lines of thought and deepen the complexity of what my writing. And I'd just like to say thank you to the wonderful folks at FYI who supported me throughout the summer, as well as those at at SPS and at Davidson College. And without them, I never would have applied to the program to begin with. And with that, if there's time, I'd love to field any questions that folks might have.
Awesome talk. Thank you so much. We have time for one quick question, and it's a great one. How can you take your equity work back to campus this fall?
That's a wonderful question. I think that the energy equity bulletin just forced me to expand my idea of what qualifies as an equity issue. And I certainly think that there are a lot of things within undergraduate institutions that are taken for granted, like, for example, people's ability to afford health insurance, educational materials, and so forth. So I just think that that was a really good lesson for me in thinking more critically about what might impede access to success for certain communities.
Thank you, and a great job on your talk.
Thank you so much, Brad.
Yes, thank you, Julia. Amazing. Next, we have Madison Brewer, our Physics Today intern from the University of Pittsburgh. Madison.
All right, hi everyone. My name is Madison Brewer. I'm studying astronomy and nonfiction writing at the University of Pittsburgh, where I will be a senior in the fall. And this summer, I was the Physics Today science writing intern. And my talk will be about the Physics Today writing, editing, and publishing process. So before you can even start to write, you have to look at your publication and who they're writing to. So Physics Today is a physics magazine. It's published by AIP, and it's written primarily for the physics community. Whether or not that means someone with PhDs, these people definitely have some background in STEM or technical fields. Many of our editors have PhDs, mostly in physics, but there are others in geology and history of science, and publish a magazine once a month and regular online content in between. So the writing process basically comes down to 3 big steps: research, writing, and editing. And we're going to walk through them using a story that I wrote for the Physics Today website about the physics of the loop-de-loop. So the number one place where we always have to start is finding a story. So that can look like reading through press releases from email alerts, but it can also look like going to academic journal websites and just clicking through their most recent publications, right? So that can be astrophysics journal, physical review letters. In this case, this one was for the American Journal of Physics. And then how do we identify possible stories? So you got to kind of get from the titles and maybe the abstracts. If this is interesting, does it say something unexpected? And can you pull a story out of it? And once you find a couple of options, you can kind of narrow down which one is going to be the most interesting, to yourself and to your readers. And then it's time to start gathering your information. So you always want to read the academic paper that you're basing your article around. And I think it's really important to take notes, whether this is in the form of paraphrasing different points that they make, or copying, pasting important sentences, so that way you don't have to look through them in the paper when you're ready to write. And you don't have to understand every single detail of the paper, especially not any of that technical math or coding, but you need to understand what's happening and why it's happening. And then if you can, it's really great to interview the authors of the paper or other people who were involved in the project or a similar project. They can give you really insights to their process that you don't read in the paper. So I always ask questions like, why did you decide to start researching this? What motivated this project? What do you hope to get out of it? What will you be doing next? And this is really helpful for this particular article. They talked a lot about making realistic research projects for undergraduate students, and also the fact that despite the fact that the loop-de-loop has been around for a long time, nobody has ever really rigorously looked at it to see what all the physics are, which they thought was kind of funny. And so that's all the information that I got out of the interview that I definitely wouldn't be able to get from the paper. And then you have your other resources. So this is going to be like Googling words you don't understand, or looking up a topic or a process that's been a long time since you learned about. And then it is time to write. So I always start by outlining, so that way I can kind of get an idea of where the story is going and what I want to say. But you need to always keep in mind your story's angles. So that's the narrative that you're weaving through. Like I said, I really used the things they said in their interview to kind of add a human exploration element, so that the reader is kind of thinking along with the researchers and coming to hopefully similar conclusions. And then I always do the introduction, the transitions, and the conclusion last, because I really feel like they put the bow, tie up all the loose ends. Your introduction is what gets people hooked onto the story. Your transitions are what keeps them reading. It wants to read smoothly all the way through. You don't want to be jumping around from topic to topic. And the conclusion leaves your readers feeling satisfied. And then it's editing. Editing is tough. Sometimes it's really hard to see your writing absolutely ripped to shreds, but it's worth it, and it will always make you a better writer. So the main things that editors are looking for is, does it make sense and does it sound good? So making sense, you want to make sure that the physics and the explanations follow the logic that you have in your brain, then that other people can pick them up. Right? Because if your editors can't understand your paper, your article, how can you expect your readers to? And does it sound good? That's really about, making sure your grammar is good, you're using varying sentence lengths. Sometimes if you read something, you can kind of tell that it's a little choppy, it needs a little work. And so that's something we want to avoid in our published writing. And then there's a lot of editing. So first it goes to the editors. There's usually 3 of them. And then once they're satisfied, then you send it to the researchers for fact checking. And once they're satisfied, then you send it to copy editing, who looks for Physics Today style rules, right? So this might be like, we don't spell out the United States, we write US, no periods. Or it might be when to use a hyphen, an M dash, or an N dash. And then finally, there's the proofreading, which is just one last glance over to make sure everything looks and sounds right. And then your story is finally posted. Easily the most satisfying part, seeing your name up there with your work and the Physics Today header. It's really nice. All right, that's all. So I would like to thank SPS, Christine, and Andrew, and everyone at Physics Today. I really had a fantastic summer, and I couldn't have had it any other way. So if anyone has any questions, I'll be happy to take them now.
Great job. So 2 quick questions. The first is, how would you approach storytelling for audiences with a scientific background for those with less exposure to science?
That's a really good question. So when you have a scientific background, you can use a little bit more jargon. So, you can use words like absorption lines and like spectra without necessarily defining them. But for people who don't know anything about science, you have to go over, like what you're getting out of a spectra, how do you look at it, and things like that. It's really just about defining words.
And question number 2 is, do you think scientists should be better trained in public communication to assist people like you who act as a bridge between scientists and the general public?
In general, probably. But we do need people in this middle step who can talk to scientists and talk to non-scientists at the same time. But I definitely think that scientists, you got to remember that not everyone else is thinking the same words and in the same language you are almost. So
Audience is very important. And thank you for an amazing talk. Congratulations.
thank you.
Yes, thank you, Madison. Our next talk is our APS Careers intern, Kurt Kleinsasser from Lycoming College.
All right, let's see. So, hello everyone, I'm Kurt Kleinsasser. I'm a junior majoring in physics and chemistry at Lycoming College with a minor in computer science. I'm the APS Careers intern this summer at APS. In this presentation, I will talk about trends in desirable applicant skills of physics degree holders. My project goal was to use APS job board data to analyze skills of physics degree holders that are in high demand by employers. I needed to create and catalog a database containing the data, quantitatively analyze this data, and examine correlations in the data based on sector and job permanence. Various tools exist to catalog and analyze such data. However, we needed a program to identify and count important keywords in the data based on specific conditions that we specify. This is possible in tools such as Excel, but such solutions are slow and difficult to implement. Rather, we chose to build our own program to achieve these goals. Some classifications, such as job permanence, are not even given by the job board. This means that we need to make those classifications as a prior step in order to analyze data based on those conditions. We used Excel formulas to achieve this, but we hope to build this pre-processing into a custom solution in the future. We chose to build our program in Python with various modules to handle user interfaces, our database system, and data conversions. Specific choices include SQLite 3, which is a fast and locally operated Python module, as our database system. I also implemented pandas, PySimpleGUI, and other modules to interface with the user and handle file conversions. The final product is a fully contained executable program that can quickly and efficiently process our data and spit out results. First, the program creates and populates the job database for the import module. Then we can use the search module to find the most common keywords in the job descriptions with filters based on word type, minimum hits, and other filters. The program can then send this data or custom keywords populated by the user to the Analyze menu. Here we can select which field to analyze, such as job description, title, or requirements, and then select which analyses to perform. This module then spits out our results, which we can export and analyze. Before we delve into results by keyword, it would be a good idea to draw your attention to the trends in job permanence by sector. You may note that temporary jobs are much more common in academic and government sectors, as postdocs are more common in those fields. Furthermore, private jobs are almost always permanent. These graphics show the percentage of the sector that contains each keyword. For example, the first keyword, assistant, appears in about 40% of all academic jobs. The terms shown are selected from those with the highest variance between sectors. Blue represents academic, red is government and national lab, and yellow is private. Some results seem obvious. Keywords like assistant, course, and teach are much more common in academia, as one might expect. Customer and product are more prevalent in the private sector because they're more market-oriented. Terms like design, develop, model, solutions, technical, and test are more common in private and government sectors because those positions are more R&D oriented, while academic jobs have a higher teaching component. Vision is more common in government fields because labs are often vision driven and there's more strategic planning. Some results are more interesting. Oddly, oral appears much more often in government and academia. Experiment is equally prevalent in academia and private sectors, but it appears much more often in government and national labs. Fusion and plasma appear much more often in government sectors, most likely due to labs such as the Princeton Plasma Physics Lab. This chart compares keywords for selected terms with low variance between sectors. Interestingly, analysis is much more common in government and private sectors than academic sectors. Compliance appears more often in government sectors, as one might expect. Unsurprisingly, weapons is more prevalent in government fields. There are small differences, but it is interesting to note that electrical, electronics, mathematical, and optics appear somewhat reliably in all sectors. These seem to be good skills to bet on. We also chose to investigate selected terms related to diversity based on sector. A notable theme here is that private sectors have consistently lower mentions of diversity in their job descriptions. Certain terms have a much higher disparity, such as disabilities, inclusivity, minorities, underrepresented, and women. We suspect that academic postings are consistently ahead in these terms due to the standard diversity language that is required by many universities. Public sectors may be required to include such diversity statements. We also found some interesting results based on job permanence. Most permanent jobs include development, leadership, management, and teaching skills, while temporary jobs focus more on experiment and research. Once again, we see a disparity with the term oral. To conclude, a high percentage of jobs in the private sector are permanent positions, while academic and government sectors have large proportions of temporary positions. Keywords oriented towards research and development, such as design, develop, model, and technical, are more prominent in private and government sectors, while terms like teaching course were more often seen in academic sectors. Experiment appears most often in government sectors and appears with similar regularity between academic and private jobs. Diversity terms do not seem to change by job permanence. The average standard deviation between temporary and permanent jobs is under 2%, compared to the 9% we saw between all sectors. The private sector did not include near as many terms as the other sectors. While our analysis provided some interesting insight, we have more work we can perform to further this project. If I had more time, I would perform further analysis based on other conditions, such as degree requirement and job level. And while our application has significant functionality, we could still extend its scope by integrating pre-processing and improving the import module to intelligently identify imported columns. I'd like to give special thanks to my mentor, Midhat, for all her help and support throughout this project, and to all the folks at AIP that made this internship possible.
Awesome job. We have time for one quick question. How will your experience change how you approach your courses this fall?
That's a good question. So I think it kind of opened my eyes towards the diversity. Results were particularly interesting to me. And as I'm a student leader in several organizations on campus, I can use those results to help guide my decision making and hopefully provide a more welcoming and inclusive environment to students in my spaces.
Awesome. And I think there's one or two more questions in the chat. But thank you for your talk. You did a great job. This is super interesting work.
Thank you.
Yes, thank you again, Kirk. Our next speaker is our APS Public Engagement Intern, Hannah Wistren.
Yeah. Thank you, Kayla and Brad. Hi, everybody. My name is Hannah Wistrand, and this summer I was honored to work in collaboration with the Public Engagement and Office of External Affairs at the American Physical Society as the Public Engagement Intern to help combat the spread of scientific misinformation, a super interesting topic. So for starters, a little bit about me. I'm a rising senior at the Colorado School of Mines and Engineering Physics. I was proudly born and raised in the Pacific Northwest as the daughter of two high school video production teachers, an upbringing that really truly inspired my interest in people, communicating, and media. And that, coupled with my involvement in service and online organizations such as SPS, is how I found myself in this position this summer. So this summer, I was tasked with determining the most effective strategy for the role that APS and its members play in the issue of scientific miscommunication. We set out to answer several main questions. Why does misinformation spread? What engages our members? How might we train our members to become better communicators? And how might we measure the efficacy of such a campaign? From these questions, we developed a trial campaign to train APS members in effective communication skills around the issue of vaccine hesitancy, hoping to be better equipped for future pursuits of political and social advocacy. When we set out to determine the best means to engage our audience and achieve our goals, it was important to acknowledge the different qualitative and quantitative means of research and data collection. Now, as an engineering student, I had lots of experience in quantitative data, but not so much in qualitative. So that was an interesting learning process for me and learning how to productively utilize that qualitative data. And so what I did was conducted research through a survey, well, several surveys of potentially interested members, as well as previous and ongoing research in areas of social media communication, misinformation spread, and vaccine hesitancy. In this research, I analyzed the interests of our members, as well as the efficacy of potential strategies, including potential training methods. The first part of our research was the analysis of the survey that was sent out to our members who had shown interest in similar projects in the past or engaged in groups of APS related to this project. We learned that 96% of these members saw the topic of combating scientific mistrust and misinformation as important, and 58% stated that they wanted to be involved right away on this campaign around vaccine hesitancy. The survey also informed us about potential concerns, including scheduling conflicts and where physicists fit into an issue like vaccine hesitancy. In researching ongoing and previous work in the areas of social media communication, misinformation spread, and vaccine hesitancy, I was able to validate the training that we were interested in for our members, citing research that shows how emotional and empathetic appeals are especially effective when combating scientific misinformation, both on and offline. Next, we turned to trying to understand how to best engage and support our members. I sought to determine where these members were currently involved in APS and their motivations for involving themselves in this project. I found that only approximately 45% came from the two forums we expected involvement from, the Forum on Physics and Society and the Forum on Outreach and Public Engagement. I also felt it was important to note the type of involvement that our members have showcased in the past. So I separated the respondents into 3 groups, defined as the group with lots of previous involvement, super excited about this idea, the group new to APS involvement, but feel particularly called to this initiative, and for that reason are represented on the engagement charts as the 60% of other involvement. And the group who indicated that they were not interested in being involved in this initiative, either due to time constraints, personal values, or genuine lack of interest. Understanding these 3 groups before interacting with our members enabled us to more effectively target these audiences, though they have originally represented a smaller fraction than initially expected, and engage an average of 52 members between both training sessions, a number that greatly exceeded our initial expectations of less than 20 on average. With all of this in mind, I worked on creating a strategy for next steps, which I presented to my APS team. I knew that my team had lots of priorities and wanted to respect their time, showing that I could take the initiative and trust that they had put in me to confidently guide them in the right direction. As a student, this is pretty daunting. You know, my entire life, I have always been in a situation of here are my ideas and opinions. If you like them, great. If not, feel free to go in a different direction. But I knew my team didn't have time for that. So I had to focus on confidently proposing specific outcomes and specific steps that we could take. Then I validated this with my research and analysis and acknowledged the priorities of both our member audience and my team as an audience. With this clear strategy, we were able to focus on our efforts on scheduling and supporting our members rather than questioning our every step. But as with any scientific endeavor, there are concerns and you run into problems. From the beginning, there seemed to be a concerning disconnect in our audience's online presence. From the survey responses, we found that while 83% utilized online communication, which this campaign relied on, only 28% indicated active involvement. In assessing early results of this campaign, we have experienced this as a real struggle. While it seemed our members left the training sessions enthusiastic and motivated, with many indicating those feelings in a feedback survey, we really haven't seen that much initiation or interaction from those same members online or with us through email and online community platforms. We plan on moving forward with several possible strategies to really get to the bottom of this disconnect, and the APS is working hard to continue this work, analyzing the efficacy of this and future efforts in the hopes of understanding how we may best mobilize our members on important topics in the future. I am incredibly grateful to have had the opportunity to work with this team on this project. I've learned so much about the importance of communication and understanding your audience as a role of public engagement. Through closely working with my wonderful mentor, Claudia Fracciola, and teammates Callie Pruitt and Francis Lakey, who so graciously took me under their wing and entrusted me all summer, I have been able to learn more about myself and my strengths as a communicator, develop my confidence, and understand how I fit into this side of physics. Thank you.
Awesome talk. Phenomenal job. So what was one thing that surprised you from your interactions with people around this topic?
I was pretty surprised by a lot of people's habits in communicating, having grown up in more of a creative environment. It was interesting to see how lots of scientists really do rely on facts and figures and numbers in their communication with the general public. And so it was interesting to see how we could shift the outcomes of conversations between people by just shifting how we talk about certain things.
Yeah, it sounds very tough. And how long were the training sessions that you did? You probably said it, I just missed it.
We had 2 sessions of an hour and a half each.
Awesome.
Yeah.
Well, thank you for a wonderful talk. Congratulations.
Thank you.
And very important work that you're doing.
Awesome. Thank you so much, Hannah. We have our next talk, Zeynep Tuna from APS Education and Diversity.
Hi, everyone. My name is Zainab, and I am the Education and Diversity Intern at the American Physical Society this summer. Before we dive into the details of my work, I want to talk a little bit about myself and why diversity means so much to me. So I'm currently a rising senior at Bowdoin College with a double major in physics and computer science. I'm also an international student from Turkey, and in high school, I studied at the United World College in Mostar, where I lived and learned with peers from 60 different countries. All of this made me really passionate about increasing the presence of women's and diversity groups, and I'm really glad to have had the opportunity to contribute to APS's work in diversity in education. So a key part of my internship this summer was dealing with a lot of data, and with a lot of data came a lot of decision making. So my first task was to help decide whether APS would continue obtaining data from the Integrated Post-Secondary Education Data System, also known as IPEDS, or switch to the new and more user-friendly interface of the National Science Foundation. My next task was to update the master Excel spreadsheet, which contains information on the number of physics degrees each institution has awarded over the years, which we call the Uber spreadsheet. In order to add the 2019 data to this Uber spreadsheet, I had to debug and extend the Python code that generates this Excel file. Next is a very important and effective tool that allows users to search institutions and see their statistics on the number and the demographics of physics and STEM degrees awarded over a 3-year reporting period, is the How Does Your Institution Compare webpage. And I was also in charge of creating Excel spreadsheets with 2018 and 2019 data in order to update this webpage. Another effective and significant webpage is the Top Educators, which shows lists of at most 20 institutions awarding the highest number of degrees in certain categories of race, ethnicity, and gender, based on average and sometimes percentage. My final task was to update these tables with the 2019 data. While working with all of this data and information, I had to sort and sometimes rank information based on certain categories of race, ethnicity, and gender, as seen from the slide. And over the course of my internship, I realized that students tend to fall into the 2 or more races category, which can sometimes limit the evaluation and analysis of our data. And needless to say, it's very challenging to fit people's identities into a finite number of categories which IPEDS and the NSF refers to as variables or dimensions. Of course, the numbers we're looking at are actual people. So as hard as it is, my job this summer was to combine the data and the categories in order to better understand the demographics of the field of physics and present this data in an effective and consistent manner. For this, we made a few decisions. We initially chose to switch to the NSF interface from IPEDS to make the process of downloading and obtaining data faster and easier. Also, in my code that generates the Uber spreadsheet, I made sure to write out full and correct titles for each race and ethnicity. Additionally, we decided to include the 2 or more races category to underrepresented minorities group. And for the top educator tables, we decided to stick with a 3-year reporting period to recognize the departments with rapidly changing demographics. Finally, we also decided to report the highest number of physics degrees granted to URM women as part of the top educators lists. And with all of these changes came a lot of documentation. So in conclusion, although we have made significant improvements towards racial and gender parity in the field of physics, the numbers of physics degrees awarded to URM and women still remain below our expectations. And this was especially apparent to me when the inclusion of 2 or more races in the URM numbers did not make a considerable difference in the spreadsheets. Another example of this is that the top educator lists that are either non-existent or lacking are mostly women's URM and URM women's tables. And we also realized towards the end that the NSF data did not include numbers of first majors or second majors, but only included first majors in their data, which created a discrepancy for some institutions' statistics and made our data unreliable. To correct this, I revised all my work with the accurate data files downloaded from iPads. And we decided to stick with iPads until NSF decides to include second major numbers in their data. Overall, this summer, I learned that data science is about making difficult decisions, and I experienced the implications and consequences of those decisions. And I'm really glad to have had the opportunity to contribute to APIS's work in diversity in physics education. Thank you for listening, and I'm ready to take any questions you may have.
Awesome talk. So question from the audience. So I realized there was a difference between the iPads and the NSF data. Could you talk a little bit about how consistent or inconsistent they were? I know you mentioned it a little bit, but.
Of course, that's a great question. So overall, when we picked arbitrary data points for data cross-checking, when we were doing the comparison study, everything seemed to be fine because in the bigger picture, the numbers did match. But for a number of institutions where it's common for students to choose first majors as, for example, mechanical engineering and a second major in physics, it did create a big discrepancy in their statistics where we only had the first numbers of first majors from the NSF data. And when accounting this information in the How Does Your Institution Compare webpage, for example, for a 3-year reporting period, it was, for example, for California State University, Long Beach, the difference in the numbers of physics degrees awarded was 20 people, which is quite significant. And we definitely couldn't ignore that. And that's why we decided to stick with iPads for now. And that was a big eye opener for us all.
Well, thank you. We got a couple more questions, which I'll let you answer in the chat, but congratulations on a wonderful talk. Awesome job.
Yes, thank you
Kayla?
so much, Zainab. We will actually take a very short break, a little bit over 5 minutes, and we will promptly start at 12:25 Eastern Time with our NASA presentations. So thank you, and I hope to see you back in just a few minutes.
And for those just joining us or those coming back, thank you again for joining us for the 2021 SPS Intern Symposium. I'm going to reconvene the session. And so we're going to go and get set up for our remaining talks. And I'll hand it over to Kayla.
Thank you so much, Brad, and welcome back, everyone. We are going to get started with our NASA intern, Gina Pantano from the University of Tampa.
Can you guys see my slides okay?
Yes.
Okay, awesome. Hi, everyone. Well, thank you all for being here. I'm really excited to share what I've been working on over the summer. So I was one of the NASA interns working in the Observational Cosmology Laboratory with my mentors, Dr. Eric Schweitzer and Trevor Oxholm. So my project was developing high fidelity simulations of Exclaim mission data. So I really want to start off by kind of going through the evolution of the universe and what period Exclaim is specifically studying. So we know about 13.8 billion years ago, our observable universe began with the Big Bang. It was very hot and very dense. And over time, the universe cooled, allowing the early nuclei to pull in electrons, forming neutral hydrogen, which is formerly known as the recombination period that we measure with the cosmic microwave background. And as the universe continued to evolve, gravity gradually pulled matter together, forming the first stars and galaxies. And the radiation from these first stars helped reionize that neutral hydrogen, and then cold gas continued to collapse on these dark matter halos, forming more clusters of stars and galaxies until right around redshift 2, when that star formation rate began to decline. And that peak in the star formation rate is known as the cosmic high noon, and that's what primarily Exclaim is studying. So some scientific motivations behind Exclaim, we really want to know what those astrophysics processes are behind that rapid decline in the star formation rate. And we can see that with the graph on the right. The red, brown, and orange data points represents the rate density from infrared data, and the blue, green, and pink points represents the rate density from UV data. We also want to know what is the typical abundance, excitation, and evolution of these molecular gases that help form stars. The total abundance of coal gas in the universe is poorly known, so that's a big motivation there. We also want to know how we can best use intensity mapping, which is a relatively new observational technique, and how we can probe these higher redshifts and study the large-scale structure of the universe, and many more questions where that came from as well. So what exactly is intensity mapping? It measures the integrated sky emission from an atomic or molecular line transition at different redshifts. And there's a lot of benefits to this because we can help track the growth of cosmic structure by seeing how these emission lines evolve over time. It's sensitive to even the faintest galaxies, so it is a blind census. We can also map large volumes a lot faster because high resolution is not required. It's cost effective because we're measuring surface brightness rather than flux. So a large aperture is not required, and we all know building telescopes can be very expensive. There's also lots of different science applications you can use with intensity mapping. There are a few caveats. Because it is a blind census, you will measure all other forms of radiation. So it's really important that you cross-correlate your observational data with previous surveys so that you can isolate those redshifts and get rid of those contaminants. And you can see a really nice simulated graph on the right. So on the left, you can see galaxy positions are shown by these red dots. And then on the left or on the right is the corresponding carbon monoxide intensity map. So Exclaim stands for the Experiment for Cryogenic Large Aperture Intensity Mapping. So it is a balloon-borne far infrared telescope that is designed to map redshifted carbon monoxide and singly ionized carbon, which are really good tracers for star formation. We have a pretty good spectral coverage, about 420 to 540 gigahertz, with a resolving power of 512. And then these are the redshift ranges that we're going to be specifically looking at. And our data will be cross-correlated with the Baryon Oscillation Spectroscopic Survey, also known as BOSS. So a big part of my project this summer was kind of piecing things together that have already been done to create this reference sky model for Exclaim. And it was really fueled by the question of how will this raw instrument data connect to these overall science questions? Because intensity mapping is new, there aren't really any data standards or pre-existing tools on kind of how to analyze and represent this data. So my primary job was kind of creating this data cube structure and adding in some Exclaim parameters. And this is what I came up with over the summer. So I created this plot in celestial coordinates using AstroPy. I also helped create individual spatial slices for each redshift using plt.mshow, which creates this intensity plot with this color scale. I worked on the storage and representation of our frequency and redshift range, which you'll see the video cycle through. And also as some Exclaim parameters, I specified our instrument angular resolution, which is represented by this yellow circle down below here, which has a diameter about 4 arc minutes. So this is kind of what it ended up looking like. It does look like static from a TV. It is a random matrix it's oscillating through. So the next big step is to integrate this with other Python code called the limlam mocker, which will actually help simulate these 3D intensity maps, which I'll show you on the next slide. But the end goal is really to create this mission reference simulation pipeline that Exclaim can build off of as the mission evolves, and they know more, technical terms with the instrument, and they can create these reference sky models accurate to what they will actually detect. So this is what an actual simulated intensity map looks like, and this was created by one of my mentors, Trevor Oxholm, this year. And this is of singly ionized carbon. And you can see as you go through the redshifts peering further back in the universe, we can kind of watch how this tracer evolves over time. So some future work, we really need to integrate my data cube structure I created with this limlam mocker and WebSky to create that 3D simulated intensity map. We also need to implement Exclaim instrument noise based off of our detector models. And then once Exclaim takes flight, this data cube will actually be used to help us analyze the data taken by Exclaim itself. And then in the far future, hopefully they can use this code and modify it for future intensity mapping missions. So before I take any questions, I really wanted to thank my two mentors, Dr. Eric Schweitzer and Trevor, for just being so great this summer and answering all my questions, and the Exclaim team for being super welcoming and encouraging us to participate in discussions, and also SPS and AIP for making this internship possible despite all the limitations brought on by COVID. It was a really great summer, and it was really interesting seeing, all of the details that go in to make a successful mission.
Awesome job. So, quick question.
Mhm.
So, you did all this work. And you said there's some future work that has to be done. When does that all have to be completed?
So that's a great question. I had the the flight timeline here. So our engineering flight's coming up in late September 2022, and Exclaim right now is going through a lot of critical design reviews. For my work specifically, it'll probably be done in the middle of next year. So that way they, have an accurate simulation of what they'll be seeing with their engineering flight. So yeah, around then.
And about how, so this experiment will go up off of the ground. About how high will it go?
About 100,000 feet in the air. So they do that to avoid a lot of the contaminants that come with the atmosphere on Earth.
Awesome.
Yeah.
Well, fantastic job. Congratulations on a great talk.
Thank you.
Yes, thank you, Gina. Great job. Our next NASA intern presentation is by Joseph Watson from McMurray University. Joseph?
Thanks so much. 1 second. And we are good to go. So my name is Joseph Watson. I just recently graduated my bachelor's at McMurray University, and it has been a pleasure to work on the Exclaim team. I got to work with Gina there at NASA, and I am going to be talking about the receiver. So now that you have an idea of what the Exclaim mission was all about, I will be able to get to tell you what we are using to be able to do all of that. And so I'll talk about the instrumentation. So we used a telescope, and we just got the question about how high we're going to go. And so that's 100,000 feet, and we're going to be picking up about 3,000 kilograms. So let's just pick up a couple cars, and that's about what we're doing. So why a balloon telescope? We could have used a ground telescope, but the downside is we would have atmospheric interference. We could use a satellite, but that's really too expensive for a short mission. We're looking at about a 5-year mission for Exclaim. So a balloon is a great option, and it really paves the way to be able to test new technologies. And so there is some new technology that we're going to be able to look at here in just a little bit. So I came on the project when a lot of the preliminary design was done. A lot of the designs met the mission criteria. The parts fit together really well. And my job is to help make that transition from preliminary design to a critical design so that we have everything ready to go, manufacture it, assemble it, test it, and eventually fly it. And so taking a look at the doer and the telescope, here you can see the receiver, you can see the optics here just vaguely. This project uses a cryogenic telescope, which means this at very low temperatures. And so here liquid helium is used to cool the telescope. And just for reference, space sits around 2.7 Kelvin, but we're actually going to be cooling the receiver all the way down to 1.7 Kelvin. They're at about 100,000 feet in the atmosphere. And so unfortunately, liquid helium will boil off, so that's going to limit our operation time. But the bigger constraint here is this large double-walled doer is very heavy. And so that really limits the size of telescope that we were able to pick up. So taking a look at the receiver, which is a bigger part of the project that I got to work on, here you could see we have microspecs, which are an integrated spectrometer. Those are fit into a detector package, which is a big part of my work. And then that goes into the receiver. And so here you can see some different temperatures that these are at. The optics are around 5 Kelvin, the receiver at 1.7, and then the readout and detector are even below that. And so a lot of the design considerations that I had to deal with were light weighting, thermal sinking, thermal expansion, and thermal contraction. All of these are very important, especially with considering it's a balloon mission, so weight's very critical. And then the thermal concerns are because of these extremely low temperatures. And so those are very important things that I had to work with through my project. So taking a look at the detector package, this was a large part of my work. So all of the parts that you see here are made out of copper, and they're actually gold plated, which helps for thermal sinking. My work was confirming and correcting a lot of the part sizes, some hole alignments, the microspec positions, and also do fit tests on all of these parts just to make sure that everything is going to work out and go together okay. Once all of that was done, I completed some very complex drawings. I wish I could show those, but the complexity of these parts is fascinating, and it took a lot of work to get all that done. And so once it was done, I did get that stuff sent out for machining quotes, and I'm looking forward to hearing back what's going to happen with those. So talking about machining just a little bit, some of the things I had to deal with were inner radii, since you can't exactly mill an inside corner to an exact 90. I also had to specify dimension tolerances, surface finishes, and surface plating. The surfaces especially are very important just for that thermal sinking, and the dimension is really important so that we get everything to the right size so it's not going to shrink too much and break. So taking a look at the new technology, this is the microspectrometer that was used. It has synthetic grading, it introduces phase delay, has very high efficiency, has capability of multiplexing, and it's also capable of ultra low sensitivity. And all of this is combined on a small silicon chip, which is a fraction of the size of a traditional grading spectrometer. And so that is the new technology that Exclaim is using. So transitioning from the detector into the readout, here you can see a wiring schematic on where the signal goes. And so the signal comes in, it goes to that detector package, and then it comes out into some low noise amplifiers, and also those bias Ts, which were another area of my work. So originally, they had a preliminary design, but unfortunately it had a multi-manufacturing methods to be able to make that. And so I designed some custom L-style brackets. I designed some custom coax cable segments. I sourced some nano-D connectors, and then I eventually combined all of these parts into assembly, and I placed 6 of these on the ring, 1 to go with each of the detectors. And so finally, once all that was done, I checked out clearances and made sure that everything would fit around nearby components. Finally, the last area of my work was working with the fridge in the ring that you can see there, that 4 absorption fridge. And so just going back to the cooling power that this has, I mentioned that the receiver is cooled to 1.7 Kelvin. The fridge there on the left actually cools down to 0.9 Kelvin, and then the detector goes all the way down to 0.1 Kelvin. And so some of my work was receiving a new design on that absorption fridge. And when I did, it had some slightly different dimensions, and so I had to make some adjustments for that. And a big change was I had to adjust those ADR braces from the other fridge to give us a little bit more clearance. Finally, I'd like to say a special thanks to AIP, to NASA, to my mentor, Eric and Tom, and to all of the interns for a great experience. And finally, I am very excited to announce that I will be continuing with NASA as a fall intern. So I'm very much looking forward to those opportunities, and I'll take any questions.
Wonderful job. Great talk. So I know a little bit about doers, and I know that what you made is super uber complex. I have a question. The thing that you're cooling, you said was roughly about like 6 inches wide. Is that correct?
Right. So the just going back up to the detector package, yes. So the hex array there, the detector package, which can hold those 6 spectrometers, it's about 6 inches.
And then, so if you're going to cool that big a mass down to 0.1, that's right. Really a whole lot of cooling power. So how much liquid nitrogen and helium are we talking about, roughly?
That's a great question. Initially, you can see this is the Dewar, and so it'll initially have liquid nitrogen, which will cool the instrument initially, or at least a previous mission did that. And then eventually that boils off, and then they replace that with liquid helium. And so exactly how much, I don't know, but it fills that whole thing. And just the receiver down there, it's about 3 feet tall. So you can imagine this is 6 foot tall and 4 foot around, 6 foot around.
So and when it goes up, how long does it stay up? Do you know, roughly?
I don't know.
Gotcha. Well, awesome talk. Thank you again for sharing this awesome research. It's super cool.
It is.
Yes, thank you so much, Joseph, and congratulations again. That's such exciting news. Thank you for sharing that with us.
Thank you.
Next, we have our AIP Center for History of Physics and Niels Bohr Library and Archives intern, Maura Shapiro. Maura?
Hi, everyone. Thank you, Kayla, for the introduction. My name is Maura, and as she mentioned, I spent the summer with the Niels Bohr Library and Archives and Center for History of Physics. I spent much of my summer researching Eunice Newton Foote, and I'm so excited to introduce all of you to her today. In 1856, Eunice Newton Foote discovered the heat-absorbing property of carbon dioxide and water vapor. In her experiment, she compared the temperature increase of different atmospheric conditions contained in glass jars when exposed to sunlight. She realized that water vapor and carbon dioxide obtained more heat than any other gas she measured, and concluded about carbon dioxide: an atmosphere of that gas would give to our Earth a high temperature, effectively predicting climate change in 1856. But despite these groundbreaking conclusions, her name and discovery were forgotten. So much so that there's no known photograph of Eunice Newton Foote, and the image that's commonly used that was found on my title slide is often accompanied by the caption, possibly Eunice Newton Foote, or one of her daughters, or a friend. So who was Eunice Newton Foote? Born in 1819, she grew up in New York. There, she attended Troy Female Seminary, which had a strong science curriculum. Early on, she devoted her life to fighting for women's rights, and both she and her husband, Elisha Foote, attended the 1848 Seneca Falls Convention, which is largely credited for sparking the movement for women's suffrage. So why didn't Foote receive credit for her discovery? This is incredibly puzzling because her work was out there. In fact, Joseph Henry presented her paper at the 1856 meeting of the American Association for the Advancement of Science. Joseph Henry was one of the leading American physicists at the time, and this would have been an incredible honor if he understood the importance of her work. Instead, he remarked, although the experiments were interesting and valuable, there were many difficulties encompassing any attempt to interpret their significance. And it's unclear why Eunice Foote did not present her own work at this meeting. Though the AAAS Constitution never explicitly prevented women from being members or presenting work, few women did. In addition, these meetings were probably a very uncomfortable environment for women, as newspaper coverage of these meetings remarked on the beauty of the wives and daughters of male scientists, and even report on a burlesque show happening at one of these meetings. In addition to this, America was preoccupied. It was facing an identity crisis, and the scientific establishment was fairly new and focused on applied science like invention. Meanwhile, in Europe, where the scientific establishment was stronger, they were preoccupied by their own work, as there were advancements across the board in electromagnetism, thermodynamics, and classical mechanics. The electric battery was invented, the wave-like property of light was discovered, and there was even a new definition for kinetic energy. Instead, John Tyndall, an Irish physicist who conducted an experiment 3 years after Foote's work was published and came to the same conclusions, received credit for this discovery for 150 years. But Tyndall should have known about Foote's work. Summaries of her paper were found in Germany and in the UK. This is an excerpt from a German publication that does misgender Foote, but her work was in Europe. In addition, John Tyndall was a member of the editorial board of Philosophical Magazine. This means he had an explicit job to scour publications looking for new and exciting science. In addition, Elisha Foote, Eunice Foote's husband, had a paper printed in this publication, which wouldn't be damning evidence if Elisha Foote's paper was not on the page right before Eunice Foote's paper in the American Journal of Science and Arts. So presumably whoever saw Elisha Foote's paper should have seen Eunice Foote's paper and presumably didn't read it or didn't acknowledge it. And John Tyndall, as one of the few members of this board, might have been exposed to her paper in this way. But there's no evidence that he or anybody else in Europe knew of her work. She's not mentioned in any correspondence, not only from Tyndall, but from any of the largely known physicists at the time. In addition, his results were treated as the first of its kind. Lord Kelvin even remarks that these results were novel. And according to his biographer, Sir Roland Jackson, it was out of Tyndall's character to flagrantly plagiarize. In fact, he was known for supporting overlooked scientists. So why no one know of her work at the time? Sir Roland Jackson summarized it best, and he had an elegant British accent that I will make no attempt to recreate, but he said, "It really is most curious, the whole thing." Fortunately today, articles, books, and even a short film that I wouldn't necessarily recommend are showcasing the work of Eunice Foote as not only a scientist, but as someone who fought for women's rights. And I'm so proud that this summer I was able to contribute to the growing body of work about her. I spent my time researching her through sorting through archival documents, reading historical publications, and interviewing experts. Because of this, I was able to make teaching guides to educate middle school and high schoolers on Foote's story and the importance of global warming and women's rights. I even was able to start writing an article for Physics Today. And in addition to all my work on Eunice Foote, I made a teaching guide about Laura Bassi, an 18th century physics professor and experimental physicist. I created a "Which Physicist Are You?" blog post for the NBLA blog Ex Libris Universum and started editing Wikipedia pages to correct the historical record. Here I am smiling next to a disheveled looking Neil Bohr at his home in the Neil Bohr Library and Archives. Thank you so much to everyone who made this summer possible, and I can take any questions.
Awesome talk. I think there might be a font error on my name. Looks like Comic Sans.
I heard it's your favorite.
Definitely not. Couple questions from the audience, though. So we have both Lord Kelvin and Arrhenius predicted man-made global warming, but had different reaction than we have. Arrhenius said man will enjoy warmer climes. Kelvin stated it is an example of humans improvising the world through technology and positive effects of capitalism. So it's more of a comment. And then we have another one. If there's time, someone would love to hear why you would not recommend the movie.
The movie takes artistic liberty and well, there's very little known about Foote, right? There's no known photograph. So it's hard to have a very accurate idea of the world. And this is like a reenactment of her, navigating the world as a woman scientist, advocating for her work. There's an argument that she has with her husband and an argument she has with John Henry about like publicizing her work that we just don't know if that happened. Henry was actually a family friend of the Footes, so it's like unlikely that they would have had this screaming match. So it's just like a dramatization of what happened, and it's entertaining the same way bad films are entertaining, but I wouldn't use that as like a research document.
Gotcha. And maybe building off Jeffrey's comment earlier, was the work ever did she ever follow up on her work? So she published this. Is there anything that she did to extend this research or promote it afterwards that we know of?
So that's a complicated question. She published one other paper, and it's surmised that the apparatus that she used in this other paper was similar, if not the same. But the other paper was about like static electricity. So she was clearly very interested in the atmosphere because it measured like how damp air, differently contributed to static electricity. But after the second paper was published, she did not publish anything else. She spent most of her time inventing. She has 3 patents out in her name and fighting for women's rights. So there's not a lot of evidence that she kept promoting her work after publishing this.
Well, awesome talk. And we do have a suggestion that you might consider also writing an article for the physics teacher as well. So I'll let you read about that in the chat. So thank you for a great presentation.
Thank you very much.
Yes, thank you so much, Maura. Our next talk is our APT intern, Alan Wright from Purdue University. Alan, you might be on mute.
Sorry about that. Hi, everyone. I'm Alan, and I work with the American Association of Physics Teachers this summer. I'm a rising senior at Purdue University, and I hope to be a high school physics teacher someday. So this internship was a really good fit for me. I didn't really have one single project that I worked on this summer. So I'm going to kind of give an overview of a few different things that I did. And notice the title of this talk too, Summer Break for Teachers. One of the things that I want you to take away is that summer is not necessarily a break for teachers. They're using this time to get better at what they do, and the dedicated and passionate teachers I had the opportunity to work with this summer were certainly using this time to their advantage. So one of the first things that I did was work on this professional development certification. And so teachers often need ongoing professional development to either renew their licenses or upgrade their licenses. But AAPT was not certified in any state to provide professional development. So this is a problem since they provide workshops and programs for teachers. So what did I do? I went around to various state websites to just find information on how to apply for certification in these states. In some states, we ended up not really needing to apply at all. You just work directly with school districts. In many states, you did need to apply through a somewhat complicated application process. And in some states, we were even ineligible to apply. But there were other ways to make sure that teachers get their credits. So hopefully now in the near future, AAPT will be able to submit some of these applications to better serve their members. This activity, although it might seem just kind of like uninteresting task to some of you, it really helped me understand the value of professional development for teachers, how it's important for them to continue improving throughout their careers, and also the importance of being familiar with all your state guidelines, even though it can be tedious to navigate some of those websites. So I've talked about how teachers need to continue to improve by attending workshops and programs. And so another one of the big things that I helped with this summer was a quantum computing workshop, which was organized by one of my mentors, Mark Hannum, and Dr. John Dell. So I helped prepare some things in advance of the workshop, but I was also really lucky to get to go to DC in person for it. You can see me there in the bottom right corner with my hat from Brad. The goal of this workshop was to help physics, math, and CS teachers integrate quantum computing concepts into their classes. And so one of the most interesting parts of the workshop to me was that we got to use real IBM quantum computers to run algorithms that we made in the workshop. In fact, any of you could too. All you need is either to download the Qiskit library from IBM or go to IBM's website, and you can use real quantum computers that they've made. But the content of this workshop isn't necessarily what I found most valuable about this experience. Instead, it was my interactions with all of the teachers who attended. They were really helpful, always willing to give advice, like let the students teach themselves, or always check in with your students throughout the day to catch misconceptions. And so watching these teachers undergo and react to the learning process at this workshop taught me a lot about creating a good classroom environment myself. I also enjoyed hearing about how the teachers got into teaching. Some were in industry first, some tried it before grad school and loved it, and some always knew it was what they wanted to do. But the point is there were a lot of paths into teaching, and they're all fine. And so I feel a lot better about finding my own way now after I finished my undergrad into becoming a teacher. The third thing I want to talk about is Step Up. And although I didn't necessarily get to do any work on this, I did have the opportunity to participate in and attend a number of meetings and discussions related to this. And I think it's just a really important thing to share with you. So Step Up is meant to address the underrepresentation of women in the physics community. You can see this graph that I got from their website. They don't have recent data, but the percentage of women receiving physics degrees is lower than you might expect. So Step Up is trying to increase that percentage. Their goals here from their website are to mobilize high school teachers to help engage young women, change deep-seated cultural views about physicists, and inspire young women to pursue physics in college. So many teachers spent part of their summer engaging with this community, learning how to make their classrooms more equitable and accessible to women and other underrepresented groups. So I encourage you all to check out their website later. But I know that I took the Step Up message to heart, and I hope that when I'm a teacher, I can be conscious of these issues and integrate some of the ideas into my classroom. I'd like to thank my mentors, Mark Hannum and Justine Heron. You guys were great this summer. I'd also like to thank my panelists at the AAPT summer meeting. You did a great job responding to questions about undergrads in physics. And I'd also like to thank SPS, AIP, and AAPT for giving me the opportunity to have this internship this summer.
Awesome talk. So if you don't mind me asking you a little personal question, what's the one piece of advice you would offer to those who may be just toying around with the idea of becoming a high school physics teacher?
Right. So I only recently decided that I wanted to be a high school physics teacher in the spring. And so what I would say is that you really just have to try it and give yourself some opportunities to see how you feel about teaching. For me, that is TAing and tutoring at Purdue. My experiences with this internship, being able to meet teachers without the student-teacher relationship was really valuable. And so if you think you're interested in teaching, find a way to try it out. You'll know it's right for you if you love being in the classroom and interacting with students. So.
And one last quick one. So based on your participation in the quantum computing workshop and doing those sort of coding things, what do you think are some of the best ways to introduce high school students to the topic?
Right. So it's definitely can be a complicated topic to introduce in high school. But there are a number of places where some of the ideas fit in. Talking about vectors, because the quantum mechanics and quantum computing is very linear algebra heavy and vector heavy, so it fits well in there. But definitely introducing, like in the workshop, we use two-state quantum systems for quantum computing. So like spin up, spin down states, instead of doing the wave quantum mechanics that some people might be familiar with from their intense quantum mechanics course in college. And so there are some easier ways to integrate that into the classroom in high school.
Well, awesome advice. I really appreciate both your answers and the talk. So thank you very much.
Thank you.
Yes, thank you so much, Alan. We have our next talk by our SPS SOC intern, Noah Johnson. Noah, the floor is yours.
Thank you very much. Screen. So my name is Noah Johnson. I'm the SPS SOC intern, and I'm attending New York University. I'm going to be a junior this fall, and I am studying physics with a minor in education. And today I'm going to be talking about a summer of outreach and captivating kids with physics. So SPS does a lot of things, but one of the core things about SPS is outreach. In fact, 78% of all outreach chapters, SPS chapters, have at least one outreach event per semester. And so one of SPS's role is to help facilitate those outreach events and make sure that everyone can effectively have fun and engaging outreach events. And so we have four main pillars of outreach: the SOC, demos, SciStar, and miscellaneous chapter activities. I'm going to be talking about each of them briefly in this presentation. So first, I want to start with the SOC, otherwise known as the Science Outreach Catalyst Kit. And the purpose of the SOC is to start or expand an outreach program, and they're all focused on one specific subject in physics. So last year and this year, the 2020 and 2021 SOC was focused on acoustics and sound in partnership with the Acoustical Society of America as part of the International Year of Sound. And so we expanded last year's SOC by adding 4 new demos, the Doppler ball demonstration, the elastic waves demonstration. We added a vocal fold demonstration with some videos, and also a soundscape experience. And so this is what the SOC would look like in whole if you were to order it from us. And this is what you also might see if you were to go to an SPS outreach event that had the SOC. And so you can see there's all sorts of stuff. There's a foam ball. And my favorite thing is the oscilloscope, which you can see over on the left-hand side. And it's just so much fun to, scream into it, and the kids love it. And so it's just a lot of fun to see your voice like pop up on the oscilloscope and actually have a visual representation of it rather than, just it being some sort of mysterious thing. And the next thing I want to talk about are the demonstrations. The demonstrations vary a little bit from the SOC. And the purpose of the demonstration is that they're affordable, engaging, and educational for SPS outreach events. What's really important is that each demo is cheap and available for anyone who wants to use them, being parents, teachers, and SPS chapters. And so they're all less than $20. And there are over 40 demos. So if you have a specific sort of subject in physics you're looking for, there's plenty of options, and you'll definitely be able to find something that suits your needs. And they're also designed for undergraduate students in terms of the level of physics that's being conveyed. And that leads me to my next point, that they do differ from SOCs. SOCs are a comprehensive group of demonstrations, whereas demos have a long write-up that are attached with them. And so it explains everything from the setup to all the physics background to everything you'll need, how to convey the physics that you're trying to teach. And so it's a lot of fun to work on that. And that was a very important part of the summer for me. And as you can see here are all the demonstrations that we have. It ranges from astronomy to electromagnetism, and everything that's highlighted in red is something that I added this summer. The third thing I want to talk about is SciStar. SciStar is a new program to SPS with the goal to have physics students use what they learn in the classroom to save the world. They're given 3 cards from a deck of 52 that have physics technologies on them, and then they're given a problem that the world faces. So for example, climate change. And they are asked to solve the problem, or at least create an invention using those 3 physics technologies. And that's kind of the project. And they get to create like a physical model using construction paper, glue, and they actually get to build something that they get to present at the end of the exercise. It was created by Randy Tagg, a professor at UC Denver, and also for a manufacturing version was created by Casey Rupke, our own intern here at SPS, who was the NIST intern this past summer. The audience is designed for undergraduate students, but this could also work for high school students with a little bit of tweaking. I also want to talk a little bit about the APT summer meeting demo competition and some Jeopardy, right? This is the miscellaneous chapter activities. So as I presented in the beginning, I organized and compiled an APT demo competition for all the SPS interns. They created these awesome demos, and I was able to present that at the APT virtual summer meeting this past weekend, actually. And it was a lot of fun, and congrats to Hannah for winning that competition. She had a great demo. And then the second thing is Jeopardy. And these are, kind of smaller, more SPS chapter internal events that are just a lot of fun. I created and revised 3 new Jeopardies, the elementary physics, general physics, and acoustics. And so you can find those all on the SPS website if you're interested in checking those out. And finally, I want to give a brief mention to the future and give some thank yous. So I have 2 years of college remaining. So I still have plenty of time. I'm going to be on the SPS e-board. And one of my goals for being on the e-board is to really stretch out our wings into the outreach world. COVID definitely hasn't helped with that, but there's so much potential in the New York City area to help bring physics to a bunch of students. And so I really want to focus on that. And this internship has also really helped solidify my interest in doing outreach and other educational careers in the future. And so I'm really looking forward to the opportunities that present themselves that I find in the next few years. And I want to give a huge thank you to Brad, Kayla, Michaela, and all the other interns for making this summer possible and making it as amazing as it was. So thank you all very much.
Great job, Noah.
Thank
And
you.
it was awesome working with you this summer. So how do you think your experiences around outreach have impacted your career?
I think that I had some experience with outreach before. I worked at a museum in high school. I volunteered there. And so I went in knowing that I liked it, but then this going in and actually like creating all these demos and learning how to effectively create and communicate science to students rather than just kind of flying off the cuff, right? Really kind of gave me some grounding, being like, all right, I know how to do it now. I know that I like to do it, so I'm going to do it.
And that leads to a question from the audience, which is, what do you think you'll do when you graduate?
I have a bunch of different options. I kind of want to apply to a bunch of different museums around the country. I love museums. They're my happy place. And I also am interested in possibly looking at Teach for America and going into, being a physics teacher for high school students or middle school students. That's something I'm also considering. So many options after college.
Awesome. Well, thank you for a wonderful talk and sharing your experience with us.
Thank you.
Thank you so much, Noah. That's so exciting. I did Teach for America, so if you're interested and you want some more information, let me know. Let's go into our next talk. We have our AIP Mather Policy Intern at NIST, Casey Rupke.
Hello, everyone. Okay, I hope you can all see my screen. Hi, I'm Casey Rupke, and this summer I was an AIP Mather Policy Intern in the Office of Advanced Manufacturing at NIST. In my talk today, I'm going to give a brief overview of my biggest takeaways from this internship by showing 3 of my projects. First, I want to give you some background about Manufacturing USA, which is the main program managed by the Office of Advanced Manufacturing. Manufacturing USA is a national network of advanced manufacturing institutes with 16 institutes across the country, as you can see on the map, each focusing on different technologies, from lightweight materials to integrated photonics, all over the board. Manufacturing USA brings together private, public, and academic stakeholders to support innovation and increase US competitiveness in manufacturing. If you notice the title of my talk, you might be asking how science policy and Schrodinger's cat are related. Schrodinger's cat is a physics thought experiment where a cat is in a closed box and we can't say for certain if the cat is alive or dead. So we can say that the cat is simultaneously alive and dead. Just like Schrodinger's cat, we want to know if legislation passes or if it does not pass. But until it does, it is also in a superposition of states and is alive and dead. We still have to prepare for both outcomes by imagining that both could be true and creating contingency plans. So my central question for this summer was, how can we create certainty in an uncertain science policy ecosystem? I'm going to be talking about 3 approaches to this question: how legislation, communication, and outreach can contribute to certainty in science policy. Although I was only in the office for 10 weeks this summer, I wanted to have an impact which lasted longer than my internship program. And I knew that strategic planning for the future could leave that long-term outcome. Here in the US, as individuals, we are free to do anything except what's restricted or prohibited by law. But government programs are the opposite. We need legislation to expand our authority and enable us to implement programs and use funding. So, for my analysis, I turned to the US Innovation and Competitiveness Act, or USICA, a bill which recently passed the Senate. The bill mentions Manufacturing USA by expanding our authority and increasing our budget. We don't know for sure if this bill will be reconciled with its counterparts in the House or if it will eventually become law, but to prepare for the possibility of increased funding and to create some certainty while we waited in limbo, I read and analyzed the legislation. As you can see on the left of the screen, I created a table with each mention of Manufacturing USA in the legislation and a translation of the legislative language to understand what our office was being asked to do. I created a strategic plan for how the office could engage with the legislation and made recommendations for how we can effectively and successfully prepare. In doing so, I hope that I created some certainty for the future of this bill. Another barrier to certainty in science policy is communication between scientists and non-scientists. I included this comic on the right to emphasize how communication is not something anyone can do on their own. It has to be a two-way street. As scientists, I feel that in our field, we are not generally pushed to know how to communicate our science to other people. So I wrote an article for NIST Connections, the internal publication, about the technical experts who volunteer their time and background in our office through fellowship programs, especially AAAS and ASME fellows. I wanted to share stories about the people with PhDs and professional experience who took leaves of absence from their jobs to volunteer and work for the government. And also I wanted to make others at NIST care about the resources that are available to them. I interviewed 5 fellows and wrote a feature article using their experiences to highlight the importance of reaching out to experts with science backgrounds to shape and implement science policy. Policy analysis and science communication are both really important in creating certainty in science policy, but without outreach and engagement strategies, science policy won't actually reach the broader community. With the right approach, I know we can reach students and engage them in thinking about manufacturing. So I teamed up with Brad and Noah and AIP to adapt the Sci-Star program, which you already heard a little bit about, to create a deck of 52 manufacturing cards for Manufacturing Day, which is an annual event on the first Friday of October to promote manufacturing. I wanted to reach students, especially high school and college students specifically, to show them that if you're interested in physics, you can work in manufacturing and apply that work with a huge impact. And because students were my target audience, I decided a fun game would be the best way to create a tangible, accessible, and certain approach to manufacturing and to science policy. Over the last 10 weeks, I learned that there is a lot of uncertainty in science policy, but there are also ways to minimize that uncertainty by planning ahead, learning how to communicate with people, bridging the gap between scientists and non-scientists, and using outreach to build support for the next generation of manufacturers. I learned how important advanced manufacturing is to our country, our economy, our society, and to the physics community, and I am so lucky to have contributed to the work of the Office of Advanced Manufacturing. I want to thank everyone on this slide for contributing to my summer experience, for all of your support and mentoring. Thank you. And now I'm excited to answer any questions you might have.
Wonderful talk, and I'm really excited to hear about all the great things you did this summer. And some questions from the audience include, do you think the US ICA bill will pass?
Oh, that's a great question. I guess I could talk a little bit more about USICA. So it is a massive bill that passed the Senate. It was 2,000 pages long with a ton of different sections, some of them relating to manufacturing, some of them relating to semiconductors, just a huge, huge bill. And in order for a bill to pass, you have to reconcile it with maybe its equivalent bills in the House. And the way that the House works is they've actually broken up maybe relevant sections into separate bills. So that is really dependent on if the individual bills in the House pass and if they can be successfully reconciled. I will say that after working with NIST and the Office of Advanced Manufacturing, I really believe in the work that we can do for Manufacturing USA. And so I hope that it passes because it would give our office a lot more authority and money to be able to enact our projects. So I'm keeping my fingers crossed.
Awesome. And a related question is Schrodinger's cat dead or alive in your photo that you used?
both. It's both dead and alive.
And then kind of building off that question, so would Congress be a better place if it had more or only physicists?
Wow, that's a great question. I definitely see the value in bringing people with explicit science and technology backgrounds into politics. I just graduated from Mount Holyoke College with a degree in physics and politics. So I definitely feel that there's an intersection there that's really important. But I don't think that just flooding Congress with a bunch of physicists is necessarily the right strategy. I think that it's more about communication, reaching out, learning from others, and learning how to collaborate with people who might have different backgrounds than you.
Including physicists, some of them anyway. Okay, so we got some more questions I'll let you answer in the chat, but congratulations on a great talk.
Thank you.
Yes, thank you so much, Casey. That was absolutely wonderful. We have our last, but not least, presenter, our AIP Mather Policy, who's actually on Capitol Hill right now, Guido Dominguez. You have the floor.
Thank you for that wonderful introduction. So, as said before, I'm Guido Dominguez. I'm the Mather Public Policy Intern. I've had the pleasure of being the Mather Public Policy Intern for the last 10 weeks for the House Committee on Science-Based Technology. And today I'll be talking about the marriage of science and politics. But because I'm talking about politics, you can't start talking until you actually talk about where your jurisdiction is, right? And so the committee has 5 subcommittees. It's energy, environment, investigations and oversight, research and technology, and space and aeronautics. And its jurisdiction is any non-defense federal spending for research and technology. So that involves things that it has under its sole jurisdiction, like NASA and NIST, but it also involves other agents and the National Science Foundation, but also involves other agencies and departments, research and technology and development funding, such as under the Department of Energy or NOAA. So the reason I wanted to do this internship is to not heed the advice of Otto von Bismarck and actually go against his word and learn how the sausage gets made. And when most people think about how the committee really operates, they think about hearings and markups where you have experts and scientists and people who are amazing in their fields talk to Congress about what needs to get done or what we can improve on. And if that's all you think about when you think about the committee, that means that the staff and the interns of the committee are doing their jobs right, because you don't see all the hours and days and weeks of work that go into making sure a committee hearing runs smoothly. And in terms of these hearings, you kind of have 2 types. You have a committee hearing itself, and then you could have a committee markup. And the difference really is that when it comes to hearing, as Julia was talking about earlier, you kind of have like fact-finding and investigative hearings where you're trying to lay out what either happened in the situation or what kind of details are in certain situations, or you also have other ones where you're trying to get recommendations for what possible legislation could look like. And then when it comes to markups, that's actually when you have legislation in front of you and you're going through the amendment process and the committee is trying to either approve or deny a specific bill so that it can go onto the House floor and eventually become a law. But when you think about that, you don't really know what an intern does in this entire space, especially because you only really think about what happens in the outer facing aspect. So this is really how I felt when I was starting the summer. And I'm glad now after 10 weeks, I can finally tell you what I did. So my involvement as intern is really supporting the committee in its hearings and its markups, but also attending hearings and markups for other committees, not only the House side, but also on the Senate side, that are relevant to the committee's jurisdiction. Here's a few examples of committee hearings that we held in the House Science Committee. The first was under the Environmental Subcommittee, and it really went over extreme heat in the United States and was really pertinent over the last few weeks, especially what we saw kind of in the Pacific Northwest, but other areas of the United States, where we see that there's extreme heat causing a lot of negative health outcomes for the individuals living in these areas. I had the opportunity with my fellow interns on the committee to actually write the charter for the committee, which goes over the background, the purpose, but also creates recommendations for our members, not only for what we can possibly do to address the issue, but also questions that the members actually asked during the committee hearing. And that was an amazing experience. The bottom one is a full committee markup of a bunch of letters and numbers that make no sense, but it's actually the same Schrodinger's cat dead or alive question, because 4609 is the NIST for the Future Act, which is a part of the USCIA Act, that was kind of broken down only for NIST, and increases NIST allocation of funding by 50% between 2022 and 2026. And on the last one was an investigative hearing into how what the FCC did in terms of bidding its 24 gigahertz spectrum for 5G, which we all have in our phones, actually has negatively impacted the ability of satellites to create predictions for weather, and what we can do in the future to prevent those negative impacts on NOAA and other satellites. I also had the opportunity to have independent research projects, and particularly was able to work under the subcommittee for energy on things that really interested me. As a physics student and as a member of my generation, we oftentimes think about how big of a problem we have with regards to climate change, and how it's almost an insurmountable task, and how that if we don't act now, we're going to miss our climate targets and have significant negative impacts for generations to come. And it was really amazing for me to be able to work on the Department of Energy budget request and look at the renewable energy offices, particularly the Building Technologies Office and the Wind Technologies Office, where there's a doubling in the funding for the Wind Technologies Office and an emphasis on electrification for the Building Technologies Office. I was also able to work on some stuff that's in the news right now, right? The Infrastructure and Investment and Jobs Act, and go through all 2,700 pages of it and see what parts were relevant to the subcommittee on energy and the subcommittee on environment, and write a summary about those relevant provisions. And it's been an amazing experience so far. And that's really why I feel like Kermit here on the right after going through my summer. I feel like as a physics student, again, as I said, you see kind of the gloomy prospects that we have in the future. And at least over the last 4 years, have seen what happens when we ignore science. But now, after working for the committee, I'm more hopeful now than ever that we can work together to address the issues, and not only address the issues of climate change and extreme heat, but invest in high risk, high reward research that'll get us into that next generation and that next frontier. So a couple of examples of why I'm really excited are the NSF, DOE, and NIST for the Futures Act. The first two passed the House with overwhelming majorities, and we're going to go into reconciliation with the Endless Frontiers Act from the Senate. The NIST for the Futures Act had its markup last week and passed the committee again with flying colors. The NASA fiscal year 2022 budget has an increase in $2.4 billion and was the largest budget request that has ever been proposed. And we can see with the Infrastructure Investment and Jobs Act that is focused on grid reliability, renewable energy, carbon capture, and other aspects, that there's a big commitment from Congress to put our best foot forward and actually admit that we not only admit that we have a climate crisis, but do something about it. And so because of this amazing experience, I just want to thank everyone that made it possible. John Mather, who helped kind of start and helps fund this part of the internship program, Brad Conrad, Michaela Cleaver, and Kayla Stevens, and my SPS family and all the other SPS interns. This summer would not have been the same without you. And then Evan Brooks, who's the research assistant for the subcommittee on environment, and more importantly, has been a mentor to me. Thank you.
Awesome talk. And you did a whole bunch this summer. So first question is, to what extent did your work on climate change issues touch upon your experiences at Pomona?
There was actually an interesting overlap going in. So I study fluid dynamics at Pomona specifically in my research, and I do some research on sphagnum moss, which is kind of one of the most important plants you might have never heard of, but it accounts for 20% of the world's soil carbon. And so in terms of that aspect, it'll actually be an accelerator as we see a lot of these moss bogs defrosting and decomposing, adding carbon into the atmosphere. But in the inverse side, I got to see a lot on what we can do on the environment side to preserve these environments that have a lot of carbon capture potential in them or carbon stored, but also what we can do artificially, because there's a lot of aspects and sectors that can't electrify easily. So let's talk about industry, for example. That's an area where you do need to have these same forms of carbon capture, research and development, and make sure that you're actually removing carbon from the atmosphere to reach our climate goals.
Yeah, and that kind of touches on the idea of where science and policy come together, which is the title of your talk. Mm-hmm. So what do you think we miss out on as a country and as a group of people when they don't quite work together as well as we want them to?
Yeah, when science and policy don't really meet eye to eye, we miss out on two fronts, I think. We miss out on the great ideas that you get just from conversations between two kind of areas that aren't really seen as similar or on the same plane. But you also miss out on investing on the future, right? Like when we don't have investments in research and technology, when we don't have investments in just general science that we don't know where it's going to go, we are missing that next great discovery, the next leap and bound to be able to move forward, right? And if the human race is all about moving to that next thing, when those conversations aren't happening, we all miss out.
And briefly, last question. So for those of us that are non-policy wonks, what's the difference between authorization and appropriations legislation?
In terms of that, I'd have to go back and ask my mentor a little bit more specifics, but you actually have the authorizations of appropriations within an authorization text. So I think, and I might be wrong here, you get a little bit of the authorization gives you the general structure of the way the funds are supposed to be spent, but it has no teeth if there's no appropriation language within it. So you can authorize, for example, NIST to have specific programs and have specific aspects of those programs that they need to satisfy, but if they don't have the appropriations, they don't have the money to do it.
Great answer. And I wanted to thank you for an awesome presentation and all of the hard work you're doing on the Hill to make sure that science and policy really get to work together.
Thank you very much.
And so I wanted to, maybe I could ask all the interns to turn their cameras on real quickly. It's with great pride and sadness and happiness all at the same time that I officially close the 2021 SPS Internship Program Symposium. That does not, however, stop the fun that you've had and the connections you've made with each other and with your mentors and those institutions. And you are always a part of the SPS and AIP family. And it's our hope that you will continue to join us year after year at future intern symposiums and continue to help make the world a better place through physics and astronomy and the physical sciences. So this is the saddest thing I do all year, so I'm going to miss you all very much. So congratulations on a great talk. Kayla?
Yes, congratulations. And I would like to thank each of the interns for all your hard work you put in this summer, as well as your mentors and the host sites. You are all what makes this program what it is today. And I hope that you are just as proud as we are. I hope this experience and the relationships you built with each other and your colleagues will continue to have a special place in your heart and your career into the far future. I would also like to thank everyone that attended the symposium and participated. Please note that this symposium has been recorded and will be posted on our YouTube channel. So follow us at SPS National and share with your family and friends, and we will see you next time.
So thank you, everybody. And to any mentors that are in the audience today or watching this, thank you for making this program special and possible.
Yeah.
So I will see you all again next year.